Hi guys, me again. Little video about the Atomium in Brussels, but an important video though. What is the Atomium? Well, I guess you can see it right here now with those video suggestions, but here on my laptop you can see it again. It's a big structure in Brussels. It's built for the World Fair of 1958 and it's made out of 9 balls interconnected. Over here we have a smaller model, same shape though. Why is the Atomium so important? Well, let's start off with a little lesson in chemistry. Over here we have an iron atom and a chromium atom. You might say, well, those are fantasy models. If you're new, you might think that. If you're a subscriber, you know I'm very serious about my work. Why is this an iron atom? Well, it has the right size, it has the right atomic weight, and it has the right number of electrons, which can create a chemical bond. Same reason, same counts for this chromium thing. How did this work? Well, this is the benchmark, just a small recap. A benchmark carbon made out of 12 nucleons. You can count them, but only the ones on the outside, meaning that triangle, this 3-legged pyramid on this side, on that side, and these in between. Only those spin, and those make up for its weight. So the atomic weight of 12 U's is created by 9 spinning nucleons, and I only count the spinning nucleons to establish the atomic weight, which means I have 9 and I have to multiply it with 1.333. I have to add 33% to get from 9 to 12. Just for checking, here's oxygen made out of 12 Q-tips, 12 nucleons. Every Q-tip is 1 nucleon. Only the spinning ones on the outer perimeter, which means 4-legged pyramid here, 4-legged here, and 4 in the middle makes 12. 12 have to make up for a weight of 16 U's, 15.99, so I say 16, which means I have to add 33% to that 12 to get 16. So that's the system. I have iron here, iron atom, same thing. I have 24. You can see that squared parameter, that square thing, that's 24. Let me make it right there against the wall. There you are. Stay there, don't fall down. Expensive telephone. Squared of 1, 2, 3, 4, 5, 6, 7, 8 times 2 times 3, 24 fully exposed nucleons. 24 points for that. Upper line 24. Then we get these 3, this formation of 3, which is a bit recessed, means I count them half. Well, the total of those is 1, 2, 3, 1, 2, 3, 1, 2, 3, also 24, half exposed. And even further within are those blue ones, which are from a previous shield, but still they have some interaction. I'm going to count them for a quart, so a quart is 6. Total 42 plus 32% makes an estimate, just an estimate, of 56 U's. And indeed, iron has an atomic weight of 56. So that's why I think this is iron. Now, if you look at the valence, well, I can get my gear system, but hey, you have to take my word for it. 1, 2, 3, 4, 5, 6, 7, 8, 24 spinning protons. But since this square thing in the middle is a bit elongated, the core of this iron thing is indeed this atomium shaped thing. And you can see it's crammed with 9 nucleons. So those outer members, those outer ribs of that cube are overstretched. They're really overstretched, which brings the outside, this one and that one, a bit more to the outside, lesser shielded. So there's a little electron on top of that thing, which has some valence then. 2 points which have a bit more valence than the other ones. So that makes 24 into it's 26. Now if you get this 4-part, we use 4 parts to expand an atom from, say, this at 4 parts, which happens in reality, which happens in the universe, where you make a nuclear reaction. You can expand it to chromium, and then again another layer, another shield, and expand it to iron. And you see on top of those 4 parts is the one holding them together. 4-part, we got here a nucleon, more detailed shape. You can see 1, 2, 3, 4 on each side. 4 dockings, 4 places where another nucleon can connect. So that's how you get a 4-part, and that's why on top of one of those is an electron, which has some valence, if not shielded. Well, in this case, the adjacent ones are neutrons. They don't lash out the way protons do. They cannot shield it, and especially in those 2 cases, that electron protrudes a little. So that's my explanation for having 26 instead of 24 electrons, which can make a chemical bond. So it's a bit out there, but in reality it's not that important. 1 or 2 protons or neutrons adding or subtracting doesn't change the global size of it. It's the size which is important, of course. But that is for me iron. Chromium atom, same thing. You can see this is much simpler. You have these 4 legs, 4 protons in orbit. Times 6 is 24. That's chromium for you. It's a very smooth surface. This is actually as flat as it can be. This too, because of those, as I said, those ribs are overstretched, opening these pyramids a bit more, making them very smooth surface, which gives us a total weight of 36. 36 exposed plus 30% is 40 HUs. Chromium has a weight of 52 Us, but you know, it's an estimate. The valence, however, was spot on. We've seen the valence, 6 times 4, 24, spot on. The shape is smooth as silk. It can make a spit shine finish. That's chromium for you. No doubt that is chromium. So that's a small introduction. But now the more important stuff, the atomium in Brussels. So the atomium in Brussels, Belgium, is an object, and we've seen it on the computer again. Atomium, there you go. Big ass object, stands over 100 meters tall in Brussels. In fact, 102.705 meters high. The scale of it is 165 billion to 1. So we know, if we calculate these things, we can make a simple calculation, then we know that the object the atomium represents has a diameter of about 0.62 nanometers, or 6.2 angstroms, but 0.62 nanometers in diameter. That's the object the atomium represents. Now, that's one fact. I cannot change it. That's not what I make up. It's a fact. You can find it on the internet, the scale. You can find the height too, and you can take a measuring tape if you will. So the atomium represents an object of 0.62 nanometers. Then we have IBM. IBM had a wonderful, they created a 1-bit memory made out of 12 atoms. I'm sure you've heard of it. It's aligned 2 rows of 6 atoms. And those 2 rows are made of iron atoms. They are magnetic, so thus they are iron. They have a length together combined of 6 nanometers. So 6 atoms have a length of 6 nanometers, which means the diameter of one of the iron atom is 1 nanometers. Again, I didn't make this up. You can find it on the internet. You can find it on the website of IBM. I don't make these things up. These are true. atomium represents an object 0.62 nanometers and an iron atom is 1 nanometer in diameter. And now we're going to look at my own atom model, the Van Kamenen atom model, and it is indeed my own atom model. It's registered as intellectual property, should have, because it's the most detailed and most advanced on the planet. It's not a joke, it's the reality of it. I've taken this piece of measuring tape and I measured 23 centimeters in diameter for an iron atom. 23 centimeters. I've also measured the core of that iron atom because, well, don't fall. See the atomium, then one shield added, you get chromium, add another shield and you get iron. This is 23 centimeters in diameter, this is 14 centimeters in diameter, and which means iron 23 atomium shape is 14 centimeters. Calculate, and then we find that indeed if iron is as IBM says 1 nanometer in diameter, we will find that this atomium shape has a diameter of 0.61 nanometers. Surprise! The atomium represents an object of 0.62 nanometers. Well, small difference, it's the same thing. So this indeed is what the atomium represents. What's so funny about it? Well, it's a perfect example of an object, of an element, of an atom that isn't mentioned in the periodic table of elements. The periodic table of elements is based on chemistry. You need to have at least one electron in orbit to get a place in that periodic table. The periodic table of elements does not include atoms which have no valence at all, but they are there. Watch the atomium. This thing is so crammed up with those 9 nucleons that these outside nucleons, these 12 on the outside, the ribs, they can spin around. They spin around, right? They can spin around, but not like this. This is when you get a proton, when one electron stands out, has a faster circumference and then has more valence. Because it goes faster, it can create a chemical bond. This is not what happened, because that big circumference, there's no room in this thing for a big circumference on the outside. Yes, but not on the inside. So all those ribs lack any valence. This thing is impotent. It cannot bond with any element, any other element or itself. It cannot create a crystal like sand grains. No. This thing lives in solitude and it has no valence at all. And you might think, well, that's not true, because on top of this thing there can be like so, there can be an electron on top sticking out of the structure. But that's not true. If you look how this thing is made, and let's go upstairs and I will show you how that thing is made, how the atomium. Hi guys, welcome to my attic. Over here are my models, and it's the part of StarDrive, and it's called the Van Kamenen atom model. That's what you see, the Van Kamenen atom model, part of StarDrive, part of a bigger thing, but well, I guess God's master plan, that's the bigger thing. But this is just a detail of it. I'm here to show you how the atomium, how the original object on which the atomium is based, how that is created. Well, downstairs we have concluded that this is iron, that's the atomium. We know that is 0.62 nanometers in cross-section in diameter, 0.62, and that is cursive IBM 1 nanometer, and indeed that is right. What isn't right is that some people say the atomium is a crystal made out of 9 iron atoms. Well, how would you like to fit 9 iron atoms into that little thing? It's impossible. It's bullshit. Don't let people fool you. It's impossible. The most logical thing is that what I say is indeed true. Within iron there is a box shape which looks like atomium, which coincides with its size and its shape. So how do we get that shape? Well, the universe is full of nucleons. These are nucleons, and they're made out of 3 quarks. And in open space, sometimes one pops out, and we call that decay, proton decay, going from a neutron to a proton. You see, one electron has now a bigger orbit, thus going faster. Thus we notice it as an electron. It's made out of 6 gravitons, 3 quarks. Well, those things have 1, 2, 3, 4, 1, 2, 3, 4, 8 total, 8 dockings, 8 places where another nucleon can fit. So here you see Q-tips, and every Q-tip represents a nucleon. 1 in the middle in this case, and 4 on each side. And when it comes out of a star, over in a star or in other high pressure areas, they are compressed into those starting points. This one is very interesting because it has oxygen, argon, germanium, tin, hafnium, curium, all those completed shells. So that's the most familiar one. But there are other starting points, as you can see. And over here, other side, more starting points from which atoms emerge. So that's how atoms are created. And the atomium especially is now point of our attention. We see 2 times 4 in open space, stretching out, fanning out, and then catching individual nucleons, thus creating this atomium-like shape. I said it has no valence, which of course is true. You can see it is indeed crammed with 9 nucleons in the middle, which doesn't leave much space for the neutrons on the outside to decay into protons, thus remaining neutrons having no valence, not being capable of making a chemical bond. Now the corner points, say, look at argon here. The corner points, as with argon, have an electron on top. This one and this one, they make up for 17 and 18, totaling number of 18 electrons capable of creating a bond. And that's because this is a prefab part, tripod made out of 4 of those nucleons. It's a prefab part. They emerge, of course, in stars, but then they dock, they land onto, say, oxygen, creating argon, or say they land on carbon, creating argon's little brother neon. So, in this case, you have 1 electron sticking out. I have a bigger scale model of a 4-part here and a 3-part. In this case, I like the blue quarks to be part of the structure. You see, it sticks out. It sticks out because it is a tripod or a 4-pod. But in this case, it doesn't catch a tripod or 4-pod. It catches individual nucleons and therefore has no protruding electrons on the corners. So there isn't any valence in spinning protons, nor is there any valence in a sticking out of electrons. 0 valence, unique outside the periodic table of elements. Now, what's the surprising part of this? This model you see here is unique in the world. I don't have many subscribers. I don't have many visitors on my website. So not many people know of this. This isn't common knowledge. This isn't known by Fermilab or CERN or the NASA or any university, any institute in the world. They do not know of this model. I can pinpoint on these models the positions of the neutrons and the protons. I can even show you what quarks look like and what neutrons look like and what electrons look like and how gravity works. But hell, who cares? I'm just another nutter. Or maybe not. Looking at iron and the atomium. The thing is, this model is only in existence for a few years. I started to write StarDrive a few years ago. But over half a century ago, an architect, the architect of the Atomium, knew about that shape and he has the size correct. Well, that's nothing short of a miracle. I think it's a misconception to think that that indeed contains 9 of those big ass iron atoms. That's not true. But it's a miracle that an architect, the architect of the Atomium, thought of this over half a century before I started writing StarDrive. So, if that doesn't surprise you, it does surprise me, and I want to look into it. I want to know why people think that is indeed 9 atoms. It's not true, it's bullshit. Everybody with common sense knows they don't fit. And if you look at the model, you know that this indeed is the truth, that the model is very accurate. But we have a little problem here. We have a new element. That element over there has 0 valence, thus does not earn a position in the periodic table of elements. So we have to name it. Now I can think of 2 names, and that's Atomium, because that big ass thing standing 1 meter tall in Brussels looks like it. So that makes perfect sense, calling this element Atomium. Another name is Belgium, because, well, the Atomium stands in Belgium. And since many elements are gone, curium, hafnium, germanium, all and on EM, like Belgium or Atomium, I think both names are, well chosen. But you know what? For now, let's call this thing the Atomium. Let's call this element Atomium. So we have a new element in our system. Or should I say outside the periodic table. Atomium. Welcome. Hi, here am I, Atomium. So, that's it for today. New element outside the periodic table. I think it's proven beyond doubt that there are indeed elements beyond or outside the table of elements. For the simple fact that only the elements having at least 1 electron in orbit are in the table. So the ones who happen to have none, the orphans, are not in that table. And it wouldn't surprise me that the Higgs particle is an orphan as well. The Higgs particle weighs 134 times more than a single nucleon. A Higgs particle is supposedly gives this mass, but it weighs 134 times more than this. So that's not possible. I think the Higgs particle is an orphan like that little iron core there, an orphan like Atomium. Something bigger like that, something medium-sized like argon, or maybe like germanium, something of that size, but without any valence. I think that's the Higgs particle they discovered, but that's just a wild guess. What isn't a wild guess is that we have indeed a new element amongst us. Well, that's it for today. I think it's big news. I'll keep you up to speed. Bye now.